Okay, welcome folks. Today we're just going to take some notes on Ohm's law, and then we'll do a couple of examples with it. So Ohm's law describes the relationship between voltage, current, and resistance, but it only works for devices with a constant resistance. So we'll kind of talk more about that at the end, about when Ohm's law doesn't work. But Ohm's law in general is how physicists describe the relationship between voltage, current, and resistance. So let's just quickly review what those mean. Voltage, which is often referred to as potential. So that's actually the correct term for voltage is potential. In most physics textbooks, you'll see it referred to as potential. So voltage or potential is the energy difference between the positive and negative ends of the battery. Um, Now, if I'm being totally honest with you, I hate this definition for potential, and I hate calling it potential. I much prefer voltage. And the reason why is because, um, well, for number one, when you're measuring the voltage or when you're measuring the potential, you're not actually measuring how much energy is in the circuit. You're measuring something else. Um, and there's also a term in physics called potential energy, and you can find the potential energy of electric circuit, and that's different than the potential. And so it all gets kind of very confusing, um, because the definition makes it seem like voltage is the energy, even though it's really something a little bit different than that. Um, and It's different than the potential energy, even though we call it potential. Um, so I like using the water analogy to think about voltage. So if an electric circuit was a water pipe, voltage would be the water pressure inside the pipe. And so that's kind of how I like to think about voltage. Voltage is like how much electric pressure is inside the circuit. It's like how much force is behind the charges moving through the circuit. That's how I like to think about voltage. Um, Voltage is usually given by the variable V, and it is measured in volts, or abbreviated, it's usually just given a capital V. So like, for example, I might say V equals 9V. Um, that might be one way. Can you guys actually see that with how I have this set? I'm going to go like this so that I think that might show up a little bit better on this recording. We'll have to see. Current is the amount of charge flowing through the circuit over a given period of time. So, like, if you could like go down to the size of an electron and sort of like just like count the electrons as they pass through the circuit over a given period of time, you would be measuring the circuit. So, like, let's say you timed yourself for 10 seconds and you counted how many electrons would pass, um, and then you stopped. That would be a measure of the current flowing through the circuit. If an electric circuit was a water pipe, the current would be the amount of water flowing through the pipe. So again, I'm going back to the analogy of a water pipe. I think it's helpful to think of it that way, because you're probably more familiar with water pipes than you are with electric circuits. So if you think about, water flowing through a pipe, if you could measure how much water or like the volume of water that goes through the pipe over a given period of time, that would be analogous to the electric current going through a circuit. Current is usually given the variable I, and it's measured in amps, or that's abbreviated with a capital A. So for example, I equals 3A. So that might be how you would abbreviate that, or how you would write an answer if you were solving for the current. I equals 3A. Resistance is a measure of how resistant, wow, what a concept, of how resistant a material is to electric current flowing through it. So the more easy current flows through a material, the lower the resistance is. And the more difficult it is to get electric current to flow through a material, the higher the resistance is. I don't have a good analogy for resistance with the water pipe because there really isn't an equivalent to resistance when it comes to a water pipe. Right? It really doesn't matter what material a water pipe is made out of. The water should flow through it at the same rate, assuming the water pressure is the same and the diameter of the pipe is the same. Okay, so resistance is usually given the variable R, and it's usually measured in ohms, and so we use the Greek letter omega, which kind of looks like a horseshoe, to abbreviate ohms. So for example, you might write R equals 2 omega, or R equals 2 ohms. That might be how you write an answer for resistance. Okay, so objects with a constant resistance are said to obey Ohm's law. And so the multiplication triangle below can be used to describe Ohm's law. So you write the V on top, and then the I and the R on bottom. And then there's 3 equations that you can get out of that. So remember how you use these multiplication triangles. You cover up the variable that you're trying to solve for, and then what's ever left will give you the equation. So to begin with, we're going to solve for voltage. So I'm going to cover up voltage. You can see I and R are left on bottom, and they're right next to each other, so that means multiply. So V equals I times R. If instead you wanted to solve for the current, you'll cover up current, cover up I. V and R are left. Since V is on top of R, that means we're going to take V and we're going to divide by R. So I equals V divided by R. Last up, if we wanted to solve for resistance, we'll cover up resistance, and then we're left with V and I. Again, since V is on top, the equation becomes resistance equals voltage divided by current, or R equals V divided by R. Okay, and so then we can use these to solve problems about circuits. These 3 equations we can. So, for example, what is the current in a circuit powered by a 36-volt battery with 4 ohms of resistance? So in this problem, the voltage is 36 volts. The current is unknown, right? That's what they're asking us to solve for. What is the current? And the resistance is 4 ohms because it says 4 ohms of resistance. Okay, and so then since we're solving for I, our equation becomes I equals V over R, because when we cover up I, we're left with V and R in the triangle. So then we'll plug in for V and R. V was 36 volts, R was 4 ohms. I equals 36 volts over 4 ohms. I equals 9 amps. So hopefully that's pretty straightforward. We're just going to go through 2 more examples. What is the resistance of a resistor that is powered by a 40-volt battery and has 8 amps of current running through it? So volts is 40 volts, current, 8 amps of current. Resistance, that's what we're looking for. What is the resistance? So we're going to cover up R in the triangle. We're going to get the formula R equals V divided by I. So then when we plug in, V is 40 volts, I is 8 amps. So R equals 40 volts over 8 amps. So that means that R equals 5 ohms, because 40 divided by 8 equals 5. Okay, last example. What is the voltage of a battery with 7 amps of current running through a circuit with 11 ohms of resistance? What is the voltage? That's our unknown. Current is 7 amps. The resistance is 11 ohms. We cover up V. Oh, I didn't cover it up, but you can imagine the V being covered up. The formula becomes I times R when we cover up the V. So the voltage equals 7 amps times 11 ohms. 7 times 11 is 77, so the voltage becomes 77 volts. So there was some practice problems at the end of yesterday's assignment. So if you didn't understand how to do them, hopefully after me going over some examples, you get it now. So make sure you give that a try if you haven't done that yet. Let's see here. Many materials do not have constant resistances. And the reason why is because many materials heat up as electric current passes through them. And this often causes the material to become less conductive. And so, like an example of this is actually like a light bulb. So even though in yesterday's lab, we kind of showed that the light bulb was obeying Ohm's law, most incandescent light bulbs do not obey Ohm's law. And that's because the filament, the little wire part that you can see when you look inside the light bulb, as that gets hotter, it conducts electricity less. And so for materials like that, we often say that those materials are non-ohmic, and that's because they do not obey Ohm's law. And so again, most light bulbs don't actually obey Ohm's law. But many materials do, in particular, the resistors that we put in most circuits, they tend to be constant, although there is such a thing as a variable resistor. But those constant resistors, they do by and large obey Ohm's law.